For the final part of the problem, we're going to find the expectation value of the kinetic energy for the quantum simple harmonic oscillator. And we'll go ahead and begin with the ground state here. And we'll use a familiar form of kinetic energy with momentum squared here, except since we're dealing with the expectation values over here, we're going to use the expectation value of momentum squared. Luckily, we were able to find this value in an earlier part of the problem. This is the last part of the problem. We'll go ahead and cancel out our like terms. Then, so h bar omega, these units check out in terms of units of energy, so that works out. So we'll go ahead and move on to the first excited state now for the expectation value of the kinetic energy. Oops. And again, we found this out from an earlier part of the problem. Go ahead and take care of some bookkeeping. All right, the units check out here. So we took care of the kinetic energy. So now we'll move on to the potential energy. So again, beginning with the potential energy of the ground state of the simple harmonic oscillator. So classically it's position squared here, but for us we're just going to use the expectation value, which we conveniently found in an earlier part of the problem. And for the ground state, it was found to be h bar. That was a funny looking h bar, but that's okay. We'll go ahead and cancel out the omegas, do our bookkeeping here. The units appear to already check out. Look at that. Units of energy, perfect. So we'll go ahead and scroll up here. So that was for the ground state. Now we'll move on to the first excited state. Okay. Go ahead and input our value for the first excited state, which was actually 3/2. And again, we'll do some bookkeeping here. This was actually 3/4 h bar omega. The units check out. And the final part of the problem is making sure that is finding out what the Hamiltonian is for these. Now the Hamiltonian in quantum mechanics is just a fancy way of saying what's the total energy. So the total energy is equal to the expectation value of the kinetic energy plus the potential energy. And for the ground state, of course. So we'll go ahead and add those. And again, I guess it's important for me to say that Hamiltonian is not unique to quantum mechanics. I think I was first introduced to it in classical mechanics. So that's exactly what we would have expected, because whenever you do the ladder operator for the simple harmonic oscillator and starting with the ground state, which we determined earlier in the text, it was actually 1/2 h bar omega. Moving on to the first excited state. And again, I won't go ahead and write this. I'm just going to go ahead and write the values that we found up in the earlier part of the problem here, which was actually 3/2 or 3/4, excuse me. And the potential energy was 3/4. So of course, so we would expect this to be 1 h bar omega different than the first excited state than the ground state in the first excited state, because in the text it explained how how whenever you apply the ladder operator between these two states here, between each iterative state, there are a difference of h bar omega for each one. So that's exactly what we seem to get here in terms of units of energy. So exactly what we had expected for this problem.